Now we're going to look at acid-base properties of ions and salts. And so this is where we need to have an understanding of what conjugate acids and bases are. So there are some ions that can act as bases because they are the conjugate base of a weak acid. So HCO3 minus was on that list of weak bases. Doesn't look like a base, does it? It has an H in front of it, in fact. You might think, well, that might be an acid. It's an acid too, but it's also a base. So if we take this thing and we put it with water and say, well, let's see what happens if it acts as a base. It takes a hydrogen ion from the water. It becomes H2CO3 and gives us hydroxide ion. What is this? That's an acid, right? That is carbonic acid. So in this equation here, we have a base and a conjugate acid. Well, if we write that the other way around, we have the equation for the weak acid, right? So this weak acid, when it ionizes, it forms HCO3. So this was the base, and this is the conjugate acid. When we flip that around backwards, this is the acid, and this is the conjugate base. We always name the reactant acid or base, and the product is conjugate, just because that's how we do it. So you see how this works? It's this one equilibrium. We can look at it from this side and say, oh, well, this is a base reacting. Or we can look at it from the other side and say, oh, well, that's an acid. That's a weak acid. Right? This is the base side. That's the acid side. Any questions about that? So if we have HCO3 minus in solution, that has to be paired with a counter ion to form a salt. And remember, by salt we mean ionic compound. Soluble salts dissolve in water. So if we have sodium hydrogen carbonate, which is baking soda, when this solid dissolves in water, it produces sodium ions and hydrogen carbonate ions. We don't care about the sodium. The sodium just brought hydrogen carbonate to the party. Sodium's boring, doesn't interact with anybody. This is what we're interested in. When we get this guy, aqueous, this guy can react with the water and form carbonic acid and hydroxide ion. And so that's how this is a weak base. So if we have a solution of sodium hydrogen carbonate, that solution will be basic. Any questions? So this ion is the conjugate base of a weak acid. So we can think of any ion as being the conjugate base of an acid. So here's our A minus again, our generic acid thing. So A minus would be the conjugate base of HA, right? Put HA in water, and we get A minus and H3O plus. There's our acid, and this is our conjugate base. We can do this with any acid. Here's a specific example, nitrate ion. What's the conjugate acid of that? Well, acid-base pairs differ by one hydrogen ion. All right, so we take this guy and we put a hydrogen ion on it, we get HNO3. That's an acid. Okay, everybody okay with that? So all ions, anions, can be thought of as conjugate bases of acids, but not all anions act as bases. It's going to depend on the strength of that acid that it's a conjugate base of. So if we have the conjugate base of a weak acid, we're going to have a weak base. If we have the conjugate base of a strong acid, that base will not be a weak base. This solution will be pH neutral. The weaker the acid, the stronger the conjugate base. So what's going on here? So if we look at this one, so NO3, that's an anion. It can act as a base. So we put it with water, and we get HNO3 plus OH minus. Well, there we go. This is the conjugate base of this acid. Is this acid strong or weak, though? That's a strong acid. Strong acids are HCl, HBr, HI, HNO3, HClO4, and H2SO4. There's just 6 of them. Strong acids. So there are 6 strong acids, and you just have to memorize them. There's only 6 of them. You can do it. Right? So when this acts as a base, it produces a strong acid. Well, what do strong acids do? Why are they strong? They ionize completely. Right? If we write the equation for nitric acid ionizing, we draw a single-headed arrow, and we're going to get H3O plus NO minus. This is a strong acid. It just goes in one direction. So if we have nitrate ion, is it going to react with hydronium ion and produce nitric acid? No, this is not a double-headed arrow. It only goes this way. So we can write this equilibrium expression, except it's not actually an equilibrium. It's just that. Because this is a strong acid. Okay? This will take a few minutes for you to wrap your mind around. Double arrow means equilibrium, so that in that solution you have the reactants and the products both present. This single arrow means it goes to completion. Does that mean there's none of this? No, but it means there's so little it's not significant. So HCl is an anion. It's pH neutral because HCl is a strong acid. Right? So if we try to write that, write the equation for this, acting as a base, we're going to get HCl and hydroxide ion. What kind of an acid is this? It's a strong acid. So this reaction only goes in one direction. If we look at a similar anion, fluoride, this solution, a solution of F minus ion, is going to be basic because HF is a weak acid. So when HF is dissolved in water, it forms a few F minus ions and a few hydronium ions, but there's also a bunch of this present. So if we have F minus coming from, say, sodium fluoride or something like that, and we see, well, what's going to happen with that? It's going to make HF plus OH minus. What kind of an acid? Well, it's weak. So that means that this goes in both directions. This cannot make the solution basic because the reaction doesn't go that way. It's a one-way street. Any questions? Here's kind of a perplexing table of sorts. Illustration. Here we're looking at acid strength going from very weak up to very strong. And here we have the base strength. Here weak is at the top and strong is at the bottom. So here are three of the strong acids, right? HCl, H2, SO4, and HNO3. And these are their conjugate bases. Because they are the conjugate base of a strong acid, they do not act as bases. They are neutral. A solution of these ions would be a neutral solution. H3O plus can be thought of as a strong acid because it's already ionized, right? But its conjugate base is water. Well, water is not, water can act as an acid or a base. And so here we see that as we get weaker and weaker acids, the bases, conjugate bases, get stronger and stronger. Until when we get down here, S2 minus is the conjugate base of HS minus. And so this solution would be basic. I'm not really sure how helpful that is, but they're opposite. Okay, classify each anion as a weak base or pH neutral. We can always write an equation for an anion acting as a base. That involves adding a hydrogen ion. So we can write out the whole equation, or we could just write the conjugate acid. Right? So what's the conjugate acid? That's pretty crooked. Of CHO2 minus. You're just going to put a hydrogen ion on that. HCHO2. Right? So doing this, we're just going to add a hydrogen ion. We talked about conjugate acid base pairs, right? So here's our anion. Here's the conjugate acid. Is that a weak acid or a strong acid? It's a weak acid. You're like, I don't know what one that is. Oh, that is weak. So this is a weak acid. So is this going to act as a weak base, or is it going to be pH neutral? This is going to be a weak base. You can kind of think of the base and the conjugate acid as being kind of in a tug-of-war for the hydrogen ion. So a weak acid, has an attraction for the hydrogen ion, but it doesn't completely take it away. Whereas a strong acid is going to hold on to that hydrogen ion. It's like, nah, I'm not letting anybody babysit this hydrogen ion. I'm just keeping it. And they're very strong, so you can't tear it away from them. What's the conjugate acid of this anion? HClO4. Just going to add a hydrogen ion. Well, one of the earlier examples, we added the hydrogen ion to the end. So what if we wrote ClO4H? Hopefully we'd look at that and say, that's weird. It's not technically wrong, but you're probably not going to recognize that. Write it so it looks like an acid to you. Because if this is an anion, we can write a conjugate acid. Is this acid strong or weak? Strong. So a solution of ClO4 minus, is that going to be basic or pH neutral? It's going to be pH neutral. Any questions? So we can determine the pH of a solution that has an anion that acts as a weak base, but in order to do that, we need to know what the base ionization constant is, Kb. So there is a relationship between Ka and Kb. I'm going to derive it for you, but you don't need to know how to do the derivation. So here we have an acid ionizing, right? And so we can write an expression for Ka. Ka is H3O plus times A minus divided by HA. And we don't put the water in there because it's a liquid. Over here, we have an anion acting as a base. It's taking a hydrogen ion and forming hydroxide. So we can write Kb for that. Everybody okay with that? Well, how can I put these together? This has A minus and HA. This has A minus and HA. So I'm going to rearrange this guy to get A minus over HA. So I'm going to cross multiply. And I'm going to get A minus over OH minus times HA is equal to 1 over Kb. You can think of that as cross multiplying, or you just inverted the whole thing. So if I want just the HA and the A together, if I just want these guys, so I can swap it into here. I don't know that this is, I'm pretty sure this is not the best way to show you the derivation, but it's how my brain is working right now, so that's what we have to go with. So I multiplied both sides by OH minus, so this is also true. So I'm going to substitute this for that. So Ka is equal to H3O plus times OH minus over Kb. Ka times Kb equals H3O plus times OH minus. And what does this equal? Kw. So Ka times Kb equals Kw. Any questions? If you didn't really follow it, it's okay. But then you just need to trust me that this is true. Okay, so now we're going to put these things together. Find the pH of a 0.250 molar NaC2H3O2 solution. Ka is 1.8 times 10 to the minus 5. Okay, this is an ionic compound, right? We have a metal and a nonmetal. So when we put this into solution, when we dissolve this, sodium acetate, that's going to make sodium ions and acetate ions. We should be able to look at this and kind of think this in our heads. We shouldn't need to write it down, but write it down if you need to. Okay, so what is the anion that we're dealing with here? Well, it's this guy. So let's see, what does that guy do to act as a base? We take the anion, we add water, and that is going to take a hydrogen and leave hydroxide ion. So we have this anion. All anions can act as bases. If we make the conjugate acid of it, is this a strong acid or a weak acid? It's a weak acid. So this is an equilibrium. So we can do an ice table. ICE. What are our initial concentrations? What's the initial concentration of acetate ion? 0.250, right? Because this is going to dissolve, and it's all going to form sodium and acetate. 0.250. What's our initial concentration of acetic acid? 0. And hydroxide? 0, or approximately 0. So then we put in the changes, plus x and minus x. 0.250 minus x, x and x. Kb. See, writing B is just easier. So what we want to do is we want to do Kb, and then we're going to fill this in like these guys, from these guys, right? So that's going to equal x squared over 0.250 minus x. But we don't know what Kb is. We know what Ka is. Ka times Kb equals Kw. Kw is 10 to the minus 14. So Kb is equal to 10 to the minus 14 divided by Ka, which was 1.8 times 10 to the minus 5. Ten to the minus 14 is the value of KW. So when we talked about the autoionization of water, water can self-ionize and form hydrogen ion and hydroxide ion. This is an equilibrium, and the equilibrium constant for that is called KW. It's H plus times OH minus. And at room temperature, it has the value 1 times 10 to the minus 14. It's a good question. So I just calculated KB. So now I can put that in here, 5.556 times 10 to the minus 10. And I can find X. You can use the solver. You can use the X is small approximation. That's the X is small approximation. And if I double check that, that's 1.9%. So X is small is valid. What does X equal? The concentration of OH minus. They want the pH. This happens a lot. Yeah. So I put this number, which is what KB we calculated. So I put that in here because KB equals this equals that, which equals KB. And then we solve for X. Okay. Thank you for asking. I was running out of room. So I solved for X by saying, well, X here is small. I'm just going to call that 0. And I did the math. You can also use the solver, and you'll come up with a similar number. Can we take the negative log of this and get the pH directly? No, we can't. This happens a lot. It's kind of annoying. I'm going to try this. I need more room. That's our hydroxide ion concentration. What I think is the simplest thing to do is find the POH and subtract it from 14. Because POH is negative log of hydroxide ion concentration, and pH plus POH equals 14. So pH is going to equal 14 minus the negative log of 1.1786 times 10 to the minus 5. which is the same as 14 plus that. I don't want to confuse you, so I'm just going to do this once. So I've got the hydroxide ion concentration. I need the pH. The fast way to do this is, okay, I've got my concentration in my calculator, 1.1786 times 10 to the minus 5. There's my number. I am going to take the log of that, not the negative log. I'm going to take the log of that, which gives me a negative number, which is negative POH, and I'm going to add that to 14. So pH is going to be 9.0714. But, didn't mean to do that. If you prefer to think of it this way, that's absolutely fine too. So then our pH should be 9.07. Any questions? Most of these equilibrium problems that we're doing, there's not any one step that's really complicated. The one thing that could get complicated is solving a quadratic equation, right? But we've got the TI-36X Pro, so we just type it in and get the answer. Once you learn how to do it, that's not hard at all. All the other little steps are easy. It's just that there are so many steps, right? And we have to put them all together. And that's what makes it tricky. And we can't just learn a pattern. Oh, if I want to convert from grams to moles, I divide by molar mass. We can't just learn something like that because there's too many variables. There's too many different ways that a question could come up. So we have to learn the process. You learn the process and then you can solve all kinds of things. Questions? 9.07. Which anion acts as a weak base? What we want to do is we want to ask ourselves, well, what's the conjugate acid of these guys? So for all of them, we just add H+, right? So here we get HCl, here we get HBr, and here we get HF. So the answer is going to be C. It has to be a weak acid, because if it's a strong acid, it only goes one direction, it never goes the other direction. So this doesn't get a chance to show that it can be a base. So this solution will be basic, or that anion acts as a weak base. Any questions? Okay, so anions can act as weak bases. Cations can act as weak acids. Sometimes. So there's three categories of cations. Cations that are counterions of strong bases. These are going to be pH neutral because that strong base dissociates completely and the counterions don't ionize water. So things like calcium, sodium, potassium, right? Sodium hydroxide. So here, sodium is the counterion of the strong base. By counterion, we just means the ion of the other charge that's making that neutral. So a counterion can be an anion or a cation. The counterion to OH minus is Na plus. Well, when that dissolves, it dissolves completely, forms sodium ions and hydroxide ions. It does not go the other way, so hydroxide does not, so it only goes the one way. So, yeah, we're not looking at the hydroxide. We're looking at the sodium. So a solution of sodium, if sodium was trying to act as a base, it would make NaH2 plus, plus OH minus. Does that happen? No. Sodium does not react with water. Doesn't that look ridiculous? NH2 plus? I had a hard time writing that because I'm like, wait a minute, what? Well, that doesn't exist actually. Because hydroxide is a strong base. So we looked at the anions. If they were related to a strong acid, they didn't act as a base. Here, the cations, if they are related to a strong base, then they are not acting as acids. Okay, so this is pH neutral. I think that was more confusing than just reading the slide.
And it doesn't make sense in this one.
Yeah, if this thing looks weird, it's definitely not going to happen. If we have a cation that is the conjugate acid of a weak base, then it acts as a weak acid. So a cation can form from a non-ionic weak base by adding a proton to its formula. So that's where we got the Na plus, it'd be Na2 plus in the previous example. In order for this to act as an acid, it has to be able to donate a hydrogen to water and form hydronium ion plus the original cation back. So this can act as a base. The pH of a solution containing the conjugate acid of a weak base can be calculated using Ka, which you would have to derive from Kb. So we have conjugate acid, conjugate base. So if the acid is strong, the conjugate base is so weak it can't do anything. It doesn't act as a base. If we have a weak acid, the conjugate base is a weak base and it acts like a base. If we have a strong base, the conjugate acid is nothing. If we have a weak base, the conjugate acid acts like an acid. Does that make sense? We've got this inverse relationship, which is what this is trying to show us. If this is really strong, that's really weak. So if this is strong acid, these things do not act as bases. If this is weak, then those are weak bases. Down here, these are strong bases, and so the conjugate acids don't do anything. So it's only in the middle where you have two weak partners that they can play tug-of-war. When you have one that's strong, it always wins. And this guy never gets the hydrogen. I don't know if that helps or not, but... So we talked about cations that are counterions of strong bases, don't act as acids, they're neutral. Cations that are the conjugate acid of a weak base do act as acids. And then there's a third one. Cations that are small, highly charged metals. The only ones I expect you to remember are aluminum and iron 3. So Al3 plus, Fe3 plus. These are small metals. They're in that first row of the transition metals. We've got iron and aluminum's even one row above. So these guys are small. And 3 plus is a pretty hefty charge. So what happens to these guys that makes them act as acids? So here's our friend Al3 plus. And he can interact with 6 water molecules and form a complex ion. We say it becomes hydrated. So here's aluminum 3 plus, and it's surrounding itself with water molecules. This is how ions dissolve in solution. So here we have aluminum 3 plus and the 6 water molecules that are hanging around it. Well, if this runs into a water molecule, which of course it is going to, one of these waters that's associated with this can donate a hydrogen to this guy, forming a conjugate base and hydronium ion. So the Al3 plus itself isn't gaining or losing a proton, but its entourage, its groupies, are going to act as the acid. And they'll do that because of their relationship with aluminum. And that's not too much of a stretch, is it? Because water does do that to a certain extent by itself. Classify each cation as a weak acid or pH neutral. So we want to think about, well, what would the conjugate base of this be? Well, actually, let me rephrase that. Because the way they said it here is better. The counter ion of a strong base. When we think of it that way, we don't end up with weird-looking things like NaH2+. So, is this the counter ion of a strong base? Well, what would that strong base look like? Lithium hydroxide. Take your cation and slap an OH on it. Is that a strong base? Yes, it is. So this is going to be pH neutral. So this is pH neutral. What about this guy? Well, what happens if we slap an OH on it? Is that a strong base? No. Not a strong base. What do we get when this acts as an acid? You see this NH part in here? This is an amine. So this CH3 thing over here was substituted in for an for an H. So this is like NH4 plus ammonium. This is the conjugate acid of a weak base. We'll see these amines, and they can have all kinds of crazy things over here. What you're looking for is a nitrogen. You got a nitrogen here, and it usually have at least one hydrogen. And you can look at that and say, oh, that's like ammonium ion. Right? Ammonium ion is the conjugate acid of a weak base. So does it act as an acid? If both sides are weak, both sides do something. So this one is going to be acidic. And the only way you're gonna be able to remember this is by doing some practice, that's why you have homework. What about Fe3 plus? No? So that is one of these guys, small highly charged metals. And so Al3 plus, Fe3 plus, you have to memorize those. At this point, if you don't thoroughly understand how they act as acid, that's okay. That's not a big problem. So this will act as an acid because it's a small, highly charged metal ion. It's Fe3 plus. The other one is Al3 plus. Well, that answer doesn't make any sense, does it? I think that's for a different question. Because this wasn't multiple choice, this was give 3 answers. I'll have to try to remember to fix that. Oh. Maybe it does belong. No, my bad. It was asking for weak acid and I was writing acidic. I don't know why it came up with C first and then the others.
Wouldn't that be all you have to do is put a week in front of each of them?
Yeah. So, weak acid, weak acid. There, we got the answers right. Oops. Okay, so what if we have a salt, an ionic solution? We have to look at the cation and the anion and see what they're going to do. So we can have a salt where neither cation or anion acts as an acid or base. So this is going to be pH neutral. So this is going to happen when the cation is the counterion of a strong base and the anion is the conjugate base of a strong acid. So NaCl. Right? Well, Na is the counter ion in sodium hydroxide. And Cl is the conjugate of HCl. This is strong. This is strong. So these guys by themselves don't do anything acidic or basic. Calcium hydroxide is a strong base. NO3, HNO3 is a strong acid. So these guys aren't going to do anything. KBr, potassium from potassium hydroxide, bromine from hydrobromic acid, HBr. Again, their conjugates are strong. So those are pH neutral. What if we have the cation not acting as an acid and the anion is acting as a base? Well, then the solution will be basic. So this will happen when the cation is the counterion of a strong base and the anion is the conjugate base of a weak acid. So let's look at the last one here. So is this the counterion of a strong base? Well, let's put a hydroxide on it. Oh yeah, that's a strong base, metal hydroxide. This is NO2 minus, so that's the conjugate base of HNO2. So that's strong. Is this strong or weak? Weak. It's not one of the 6. This is weak, a weak acid, so then this acts as a weak base. So this solution would be basic, because this part of it acts as a weak base. Oops. Salts in which the cation acts as an acid and the anion does not. Well, then you're going to have a basic solution. So here, your cation is the conjugate acid of a weak base, or it could be aluminum 3 or iron 3. And the ion is the conjugate base of a strong acid. So let's look at ammonium bromide. Well, that's not a metal, right? We could try slapping an OH on that, and we get ammonium hydroxide. So that's just going to form, that's NH4+. That is the conjugate acid of a weak base. Br minus is the conjugate base of a strong acid. So this guy's partner is strong, so this guy doesn't do anything. This one's partner is weak, and so they both act. You can have one strong and one that does nothing, or one that does nothing and the other is strong, or you have weak partner on both sides and then they both have to pitch in. And then you can also have a case where both the anion and the cation are acting, right? So the cation acts as an acid, the anion acts as a base. Here, the pH is going to depend on which one is stronger. So a situation like this might be, well, let's look at this guy. So Al3+, what's special about that? Al3+ and Fe3+ we need to remember because they act as acids. These are small, highly charged metals. So it acts as an acid. What about this guy? Well, that is the conjugate base of CH2H3O2. Is that a strong acid or a weak acid? Is it one of the six? No, it's weak. Do you have to recognize what it is? No, you don't. It's just not one of the six, so this one is weak. So that means that this acts as a base. So this guy acts as a base, this guy acts as an acid. Who's going to win? You'd have to look at Ka and Kb. So this is a table summarizing that, which may or may not be helpful. Let's see. Are we almost done here? Okay, we're almost done. We've got 2 examples left to do. Okay, determine if the solution formed by each salt is acidic, basic, or neutral. These are salts. They are ionic compounds. They have 2 ions, right? So let's write what those ions are. We've got Na+, and we have HCO3-. Those are the 2 ions. So this is going to dissolve into these 2 ions. For the cations, the most common thing, the thing we should look for first is this a counter ion of a strong base? Yes, it is, because sodium hydroxide. So this is a strong base, so that is not going to do anything. Not going to do anything. What about this one? Is this the conjugate base of a weak acid? Well, what's the weak acid? It would be H2CO3. Not one of the 6. This is a weak acid. So this acts as a weak base. So this one's going to be basic. This one's got a whole bunch of letters in it. There's only 2 ions, though. In Chem 1A, we always just looked at the first one and we said it was a metal and then everything else. Well, that was a simplification for Chem 1A. So here, we don't have a metal up here. We've got way too many letters. We're going to start by looking at the end. Do we recognize an anion here? Chloride. So this is going to make CH3, CH2, NH3 plus, and chloride ion. Well, that's not the counter ion of a strong base, is it? So this is going to act as an acid. What's the conjugate acid for this guy? HCl, which is a strong acid. So because that's strong, this one doesn't do anything. So this solution will be acidic. KNO3, what are the 2 ions? K plus and NO3 minus. Well, is K plus the counter ion for a strong base? Yeah, it is. KOH is a strong base. So this guy doesn't do anything. HNO3 is the conjugate acid for that one. This one's strong. So this doesn't do anything. So is this solution going to be acidic, basic, or neutral? Neutral. Here we've got Fe3 plus, and we have NO3 minus. Do we recognize this guy yet? Small, highly charged metal, right? Fe3 plus, Al3 plus, just 2 of them. So this is going to act as an acid. If we don't remember why, that's fine. And here, the conjugate acid for that is strong, and so that doesn't do anything. So we end up with an acidic solution. So I think one way you can think about this is each of these has a partner. And if the partner is strong, he's like very controlling and doesn't let this guy do anything. If the partner is weak, then this original one can do stuff, right? And you can make up your own weird analogies if you want. But here, this is the conjugate acid of a weak base, so that is going to act as an acid. Here, its partner is strong, it doesn't do anything. Any questions? You're going to have to practice these. Basic, acidic, neutral, acidic. Okay, this one's just pick one. Which ionic compound forms an acidic solution when dissolved in water? We want to find something that acts as an acid. What can act as an acid? We could have the conjugate of a weak base can act as an acid. A small, highly charged. can act as an acid for the cations, right? So that's for cations. This is for anions. If we want that to act as an acid, that needs to be the conjugate of a weak base. So that's what we're looking for. It only takes one. So here, is either of these the conjugate of something weak? Got NH4 plus and Br minus. So this is related to NH3 and this is related to HBr. Is this strong or weak? This is weak. So this can act as an acid. Is HBr strong or weak? It's strong, so this cannot. So here we have one where one of the ions can act as an acid. So, yay, it was the first one. Let's just check the others real quick. Potassium. So potassium from KOH, right? Strong base, not happening. HCl, strong acid, not happening. Down here, we've got sodium is the cation, the counterion of a strong base, so that doesn't do anything. And we have HCO3 is related to H2CO3. This is a weak acid. So this is going to act as a weak base. Is that solution going to be acidic? No. Any questions?